There are several, but I want to give you some big principles that guide the questions that we are asking. One of the big principles is what's called naturalness. And the idea of naturalness actually is in all of science. In the case of physics, naturalness has to do with trying to understand very large numbers. For example, if you take the size of the universe and you compare it with the size of an atomic nucleus, you get an enormous number, 10 to the 40, which is 1 with 40 decimals next to it. With such enormous numbers, it's natural to ask how come the fundamental particles of the theory are so much smaller than the universe, or conversely, why is the universe so big? You can ask it in many different ways, but one of the ways it's asked, it's called the cosmological constant problem. Another question is, why is gravity so weak? So, for example, what I mean by the weakness of gravity, when I lift this glass of water, the electrical forces from my fingers to the glass are large enough to compensate or to overcome the gravitational attraction of the entire planet Earth. And if you think about it, this is amazing. The entire planet Earth is enormous compared to my fingers. I'm able to overcome the gravity of the Earth with the electrical forces or atomic forces that my fingers exert on the glass. So the only reason why this is possible is because the intrinsic strength of electrical forces or atomic forces is far, far bigger than the strength of gravity. Again, it's about 40 orders of magnitude, 1 with 40 zeros, bigger. That is called the hierarchy problem. And these questions, the enormity of the universe and the weakness of gravity, have been driving, in some ways, theoretical thinking for the last 40-some years. And much of the theoretical community in my field, which is called high-energy physics, has been driven by these questions. And one of these questions, the so-called hierarchy problem, has had some possible answers. And much of what many people did, including myself, over the last 40 years was to search for answers to this question, the weakness of gravity. Why is gravity so much weaker than electricity? Or why is gravity so much weaker than all the other forces of nature? To answer these questions, we came up with theoretical ideas. There is 3 or 4, depending on how you count, but the simplest one to describe in words and with pictures is the idea of large extra dimensions, which was proposed back in 1998 by myself and a couple of collaborators, Nima Arkani Hamed and Giyad Vali. The basic idea of that framework is that gravity, in contrast to the other forces of nature, lives in more than 3 dimensions. As a result, it spreads inside a space bigger than 3 dimensions. And in so doing, it dilutes its strength. It spreads itself thin, in a sense. The picture there can be described as follows. Imagine the surface of this table that represents our universe. By our universe, I mean the 3-dimensional space of our universe, okay? So clearly this is not a precise... The surface of the table has 2 dimensions, our universe has 3 dimensions, but nevertheless, imagine the surface represents our universe. So all ordinary forces, which is electricity, magnetism, the so-called strong interactions which keep an atomic nucleus together, or the weak interactions which are responsible for radioactivity, all of the other forces of nature stay in this 3-dimensional space, are confined to this table. Whereas gravity can spread also perpendicularly to the table in these extra dimensions that we usually call height. So because gravity spreads in more dimensions, it dilutes its intrinsic strength. It's like when a river, which moves, let's say, in one direction, in one dimension, spreads itself into several tributaries. So it is with gravity that this extra-dimensional space dilutes its strength. And this idea received tremendous attention, both theoretically and observationally. The big experiment that we call the Large Hadron Collider at CERN in Geneva is looking for signatures of these theories. And I can describe to you a couple of ways you can look for this. So one test is the following of this hypothesis. Imagine the surface, which represents our universe, is like a pool table. The surface of the pool table represents our 3 dimensions. Billiard balls on the pool table represent elementary particles, like the proton or the electron, etc. Now, normally when we play with billiard balls, the billiard balls collide, and when they collide, of course, they still stay in 2 dimensions. They stay in ordinary space. But the sound that the collision creates propagate also in the 3rd dimension. So even if we were not looking at the extra dimensions, just by listening to the sound that the collision of the billiard balls produces, we could infer about, what happened, the collision and the fact that some sound was emitted inside the 3rd dimension, so we could infer about the presence of the extra dimensions. So LHC is looking for the analog of that. You collide 2 elementary particles, which in that case is protons, and if there are extra dimensions, some of the energy of this collision may manifest itself by particles that come into the extra dimensions. So some of the energy that was in our universe, if you wish, in our what we thought was 3-dimensional universe, will be missing before the collision and after. Some of the energy has been carried out in a new space that we are normally not aware of. This is called the missing energy signature. You collide 2 particles or 2 billiard balls, and there is some energy missing because it went to new particles or to the sound waves in the case of the billiard ball. And by looking very carefully at energy imbalance before the collision and after the collision, you can look for the space of extra dimensions. Historically, I was made aware by talking to some of my experimental colleagues at Stanford that gravity has been tested to only distances of back then it was about 1 centimeter. This means Newton's law of gravitation, that the force between 2 particles goes like the inverse square law, had only been tested down to a distance of a little less than 1 centimeter. And this was back in 1990. So I was astonished to hear that. The original measurement was done 200 years ago. How come? So that immediately planted to me the seed of an idea that I should be brave about creating theories where the law of gravity is different at distances below 1 centimeter. Newton's, what's called the inverse square law, is not obeyed at shorter distances. So that sort of opened the door for me that I could contemplate such possibility without immediately being disproven by known experimental facts. The other thing, theory also played a role in the sense that I was looking for an explanation of the weakness of gravity. However, for several years, I didn't make the connection between those two. In fact, I wrote papers proposing new particles that could cause deviations from Newton's law of attraction, but without any reference to extra dimensions. And then finally, after a few years, my colleagues and I started making the connection, and that's how the theory of large extra dimensions was proposed. So when I started talking about this possibility in 1990, several physicists, in particular colleagues of mine at Stanford, were inspired, experimental colleagues, and we started talking about them testing Newton's law. We spoke for a long time, maybe a couple of years, with a friend of mine, Aaron Kapitulnik, and we are good friends. So we have dinners together and we drink good wine together. So it was at that setting that we started talking about these very wild and speculative ideas, and he decided to test them. And he and several other people around the world started looking. And today, the force of gravity, Newton's inverse square law, has been tested down to a distance of about 100 microns, so far smaller than a centimeter, which used to be the case. And now there is enormous amount of effort to test it at shorter and shorter distances. Now, what does this have to do with extra dimensions? Well, if there is extra dimensions, the so-called inverse square law will be modified. For example, if instead of 3 spatial dimensions you have a 4th, the inverse square law will become the inverse cube law. And if it's 2 dimensional, it will be the inverse 4th power law, etc. So that's what these experimentalists are looking for, a deviation from 1 over distance squared to 1 over distance cube or 4th, etc. And clearly no such deviation has been seen, but people are looking at shorter and shorter distances now. And in fact, there was a very nice workshop, or actually it was a school last week, where many of these top experimentalists were giving lectures to students from all over the world and to each other. Actually, there were many professors, experiment and theory, about the new frontiers, how to look for such new dimensions. And this is a very nice story because it shows you how a theoretical idea that can be described without too much mathematics can in fact connect with experiment. Now, part of the reason for that is 30, 40 years ago, it would be incredible for anyone to propose looking for such small forces at, let's say, below 100 microns. Such new forces have been looked for down to distance of 40 microns. To give you an idea, 100 microns is smaller than the width of human hair. So it's incredible that you can even conduct an experiment, let alone a precise experiment that will measure the force between 2 not visible particles to such a precision. And so why was this possible? Definitely it wasn't possible 50 years ago. Microtechnology. In other words, there has been a driving force in part because of application to manipulate things at extremely short distances. And over the last several decades, experimental physicists have been at the forefront of this manipulation of the very small. When they started doing that, their objective was not to test gravity. I don't think there would be enough money, such an effort from the physics of 40, 50 years ago. Usually physicists like to emphasize how physics makes our lives better. We have all of technology, electricity, and how useful quantum mechanics has been, lasers, etc. But there is also, of course, the converse, where technology allows physics to progress. And these things go hand in hand. So when I started to think about this in 1990s and started talking to my good experimental friends, partly motivated for social reasons, to have a good time on the weekends, etc., then I realized, oh my God, these people are amazing. I couldn't believe it. They can look at 100 microns, smaller than the width of a human hair. Yeah, just by all means do it. So they went from a centimeter, which you can visualize, to extremely small distances, and they'll be progressing further. I actually think this paradigm sort of summarizes much of, this is sort of at the highest level. It summarizes, though, the interplay between theoretical ideas and technology and experimental progress, and the back and forth. So the hierarchy problem was the problem of understanding why gravity is so weak. So the connection is, if there are extra dimensions of space in which all elementary particles that we know of, electrons, protons, all the forces, the other forces we know, electricity, magnetism, etc., are constrained to this 3-dimensional space. This 3-dimensional space we call our universe. Now, if gravity is not constrained to this 3-dimensional place, but it spreads into the extra dimensions, then it will dilute its strength and it will become weaker. Now, how weak? Well, it depends on the size of the extra dimensions. The bigger the size of the extra dimensions, or the more extra dimensions you have, the more rapidly you dilute the strength of gravity. So in fact, you can infer some relation between the size of the extra dimensions and the weakness of gravity. So that's the connection. The gravity is weak because there is a large amount of space in extra dimensions inside which gravity dilutes its strength. That's the connection. So what used to be 40 decimals now translates to how many extra dimensions you have and how big they are. They cannot be ultra small, but they can be even as small as 10 microns, 100 microns, and still explain the dilution or the weakness of gravity. So naturalness came because you transcribe the problem which looked like a 40 decimal problem to some geometric problem that you can imagine solving. So that's an example of an approach to the natural. Now, I don't want to get, because it's not my field, but in other fields, for example, in biology, in some sense, Darwin's theory made many of the biological wonders. So what seems unimaginably complicated, like a human being where millions of things have to work synchronously, very precisely, can think, the heart, the mind, everything. These become a natural consequence of what's called evolution. Again, it begs for a mystery. You start, if you wish, with a theory that has nuclei and electrons and atoms, and all of a sudden you have this enormous universe that supposedly follows from the same equations that have these tiny nuclei, etc. How can this be? This problem has many, many facets, and I cannot do justice to it. I'll just tell you that there is no solution to this problem. At least there is no solution within the usual framework that science proceeds, where you write down the laws of nature, which means some equations that dictate how the universe works, and then you can derive that, therefore the universe is large. There is no mathematical theory of this. There is a very controversial approach to this problem, which was proposed back in 1987 by more than one person, but in particular a very well-known physicist called Steven Weinberg, who just passed over a year ago. The basic idea there is embedded in what's called the idea of the multiverse. But before I take you back to what's the multiverse, I want to draw an analog. And this goes back again to some ancient Greek physicist called Aristarchus. Aristarchus was one of the first people that believed there were many, many solar systems. That was not a very popular idea either at the time of Aristarchus or even in 1600, when what we call modern science emerged. Most people, even by 1600, believed that there was only one solar system. That was it. So then, in the context of this, many mysteries appear. If you believe there is one solar system, it looks amazing that solar system, in particular the planet Earth and the Sun, the distance between the Earth and the Sun, were made just perfectly to allow the conditions on Earth to be friendly to our existence. For example, if we were a few percent closer, a few percent further than the Sun, the Earth could either boil or freeze and we wouldn't be around. The chemical compounds that we see on Earth are just exactly what we need to exist and to flourish, etc. So it looks like a miracle in many ways, considering how much it takes to have life. And this point of view is very popular. It was obviously also popular with the church. There is some deity that really cares. That's why everything was made perfectly for our existence, etc. Then in 1600, there was a priest called Giordano Bruno from Italy who really believed in Aristarchus' ideas. And he started discussing them in public, and eventually he was burned at the stake for his beliefs. He was burned at the stake in 600. Galileo was almost burned at the stake around 1630s. Galileo died in 1642 and Newton was born in 1642. So that was really the beginning of the Renaissance of science. And so many ideas, in many ways, they went back to what Aristarchus actually could argue that the lights that we see in the sky are actually solar systems. And because they are so far, you can't tell that they are moving, but they are moving, etc. So they started going back. And then Galileo, of course, invented or co-invented the telescope. And people started looking at planets which had moons around them. And then they said, okay, it looks like things like our solar system actually are probably out there. And they started making observations. So modern science. And now, of course, if you ask anybody, of course, there is many solar systems. In fact, if you take the number of galaxies, there is about 100 billion galaxies. And each one has about 100 billion stars. 10 to the 22 stars, again, and one with 22 zeros, stars in the universe. And most stars have planets. We are not unique. So the chances that when you have such a huge number of stars, that chances that in some of them there are friendly conditions that allow life like our own, or maybe quite different than our own, to exist is extremely likely. It hasn't been proven because we haven't made an observation. It hasn't been proven yet, but I think most scientists believe that it's very likely that conditions similar to our own or even different can allow the evolution of intelligence and life in other places. So notice what happened, that what used to be unnatural or required great care, namely the occurrence of life in the universe, is by changing your perspective and of course encouraged by observations, it became something not just palatable but very likely. So that's an example of how a change of perspective converts something that looks miraculous to something that looks natural.